Oh, Lord, we're only a little bit late, but we're doing this all for your glory. So I ask you, Lord, to make this thing work. I've had all this technology problems, but we're just going to trust in you, Lord, that this is all for your glory. In Jesus' name. Okay, those that are watching the video, I'm looking at the screen here trying to get all synchronized. I just wanted to remind you that all of the PowerPoints and the updated materials should be on the Legacy Ministry College Moodle, but you can go to my website, creationrevolution.net, and download the latest stuff. And the reason I suggest you do that is I made downloads about about an hour before this class. I was working all afternoon, so there's going to be a lot of extra stuff here that you might not have already. Well, I want to go back to what we ended with last time, if I can find the end key. Sorry, I'm a little rattled right now. I'm not even using the right control. There we go. Okay. Last time I ended up talking about that scientific notation is very useful for writing large and small numbers, but there's also one other thing it's useful for. Scientific notation, you write one digit, possibly a decimal point, maybe other digits after the decimal point. You can have just one digit, or you can have 1.3257, or you can just have one. And the difference there is something that's called precision and accuracy. Let's make sure it's still recording. Yes, we're still recording. Okay. When you're doing measurements, you may have junky equipment or you may have good equipment. So this is something that's different from ordinary conversation, where you use the word precision and the word accuracy as synonyms. In science, they're not the same. In science, accuracy is how close something is to its actual value. So there's another one of my little dumb memory aids. Accuracy, actual. So who tells you the actual value? Somebody that's got fancy equipment that's a whole lot more expensive than yours is. So somebody says, okay, the correct speed of light is 3.0. I can't measure that. So okay, I do an experiment, and I find out, am I close to what they said, whoever they are, the authorities? That's how you know that you're being accurate. But accurate is not the same as precise. In science, precise, notice I've got these highlighters, ACC and AC. Accuracy is actual. Precise is repeat. So the PRE and the REP go together. How precise you are is how closely you can repeat your measurements the next time you do them. So if you've got junky equipment, not very good. If you have good equipment, okay, maybe it's pretty good. So the example I'm using here is, suppose you're trying to measure the length of something, and you've got a stick, and you say, I don't know, it's that long, that's about a meter. Well, you could put it up against an object and say, yeah, I guess it's about a meter. So when you're writing scientific notation, you'd write 1 times 10 to the 0 power. You could actually leave off 10 to the 0. 10 to the 0 is equal to 1. So if you have a junky measuring device, that's what you say. But if you've got a little better equipment, suppose I have a stick with a marking every 1/10 of a meter, every decimeter. Now I could use that stick and I could say, well, okay, to the nearest 1/10 of a meter, this thing is 1 meter long. What that means, I could say it's 1.0. That's to the nearest 1/10 of a meter. If I have a better measuring device where I have a lot of markings on it, suppose I have a marking every 1/100th of a meter, then I could report the measurement to the nearest 1/100th of a meter, which is, instead of just 1 times 10 to the 0, or 1.0 times 10 to the 0, I could now write 1.00 times 10 to the 0. The more decimal places you report, the more precision you're claiming, the more you're saying, I have good equipment that's letting me get good readings. You can't necessarily say that because something's precise it's accurate, and you can't say because it's accurate it's precise. Suppose I have a meter stick that's all bent and twisted. Well, I might happen to come up with a correct measurement with that. It might be accurate, but the next time I try, I'm probably not going to be able to get the same reading. So it's not very precise. So I just wanted to point that out about precision versus accuracy. That's part of what scientific notation is used for. So if you have 1,000, well, is that 1,000 to the nearest 1,000? Is it 1,000 to the nearest 100? 1,000 to the nearest 10? 1,000 to the nearest 1? Well, with scientific notation, you can tell. An awful lot of this stuff is because of authority. Somebody told us and we said, yeah, okay, I guess I know what they're talking about, so sure, I'll go ahead with it. Okay, so far so bad. I mean, so far so good. I need to go to the back of the room and flip to the next PowerPoint thing. Excuse me a second. I don't dare try to pause it. Okay, let's talk about how science works. Experimentation. People just don't seem very clear on what science really is. Was that somebody coming in? Sometimes people pretend to be certain about things when they really aren't. And nowadays we keep hearing, trust the science, follow the science. That's ridiculous. There's no such thing as trust the science, because if you do that, you're never going to make any further progress in science. You have to question everything. So Aristotle, for instance, once said, he said several things that he thought were correct. Boy, this is weird. I'm looking at my screen and it's going woo. Anyway, I got to get a better camera, y'all. Aristotle said several things that he thought that made sense to him. He said that the stars had to all be the same distance away, and the Earth was the center of the solar system. He said heavier objects always fall faster. He said all objects possess an innate tendency to come to rest and then stop. Well, Aristotle was wrong. We now know that, but at the time he was the big authority. It's like, now we say don't question the science. Back then they said don't question Aristotle, the man. So he also said there's no such thing as atoms, and we're going to talk about that probably in about 2 weeks or so. It was so highly regarded that scientific progress stopped for about 2,000 years. Remember, Aristotle was the tutor of Alexander the Great, not Alexander the Pretty Good, Alexander the Great. So he conquered his whole known part of the world, and when he did, he spread what he had learned from his tutor, Aristotle. And so this was accepted as fact for about 2,000 years. In America, much of our culture comes from the ancient Greeks. Asia, North Africa, and southeastern Europe, that's where Alexander the Great's kingdom was, and that's where a lot of our basis of you said there's no question about this. Well, we could likewise kind of be certain about and intuition, forget it. That's not part of science. We want to do. That's some of the things. When Aristotle said that the stars are all the same distance away, the first time anybody was able to observe believe the 1700s or so, Aristotle said, I can't see any difference in the position of the stars, therefore there is no difference in the position of the stars. That's a pretty arrogant attitude. If I can't see something, it doesn't exist. The first time to detect that is when really good, powerful microscopes were developed. It was the center of the star. Well, Copernicus falsified that mathematically, and Galileo falsified it observationally because he made a telescope. He didn't actually invent it. There was a guy named Hans Lippershey who invented the telescope. Galileo just read a description of it. He said, oh, okay, yeah, I can make one of those. And he did. Now, later on, Isaac Newton improved significantly on the telescope. But Galileo, the first time he pointed his telescope at the sky started to see things that nobody else had seen before. And also, Aristotle said heavier objects always fall faster. Well, Galileo, this guy, he was, true Renaissance man. Galileo, the story goes, went up to the top of the Leaning Tower of Pisa, strapped two cannonballs together, and then also took a single cannonball. And Aristotle has said heavier objects fall faster. Well, okay, look out below, however you say it in Italian. And he pushed out the single cannonball and the double cannonball at the same time, and they fell at the same rate. Aristotle's problem was he didn't think about air resistance. If you have something like a feather and a hammer, obviously they're going to fall at a different rate on Earth, but that's actually an experiment that's been done, and I think I have a link in this paper to where you can go look for it, or you can just go on YouTube. On the moon, they decided, let's try that experiment. They dropped a hammer and a feather at the same time, and they fell at the same rate because there was no air resistance. Aristotle also said that all objects to come to rest. They're going to slow down and stop. Newton said, wait a minute, no. We can do a little logic on this and experimentation. So if I roll a ball down a rough surface, it stops pretty quick. Let's smooth the surface. Oh, it goes further. Let's smooth it some more. It goes further and further. Okay, applying logic and observation, if you could get it smooth enough, no friction, then it's going to keep going forever. That's the basis of Newton's first law of motion. And Aristotle said there was no such thing as an atom. Well, believe it or not, that wasn't falsified until after the 1800s. It was a long time. There was another guy back then, a fellow named Democritus, that said, oh yeah, there have to be these things called atoms, but Aristotle was the man, and so he said, no, that's wrong. So, sorry, Democritus, you don't get any hearing. Doing science. It's not that there's the scientific method, there's scientific methodology, but you start by noticing something. Oh, the grass is green. And you ask a question, why? Why is the sky blue? Or why does that happen? Then I require a science project from my students every year, and I insisted, part of your grade is you have to do research, you have to tell me where you found information. And if you're doing science, you don't waste time. Suppose that you want to know everything there is to know about the life cycle of the Malaysian tree frog. You can move to the jungles of Malaysia and live there for 20 years, or you can save about 20 years by looking up what other people have already found. So I'm not saying that everything you read out there is perfectly reliable, but it gives you a good background, a good starting point, shows you what's been tried already, what didn't work, some ideas about what, and then what you've read and observed, you come up with a hypothesis. I think that if I do this, that will happen. I think this causes that. It's a cause and effect relationship is what you're looking for. So you come up with, you devise some way that you can use your senses to test the hypothesis and find out whether it's really reasonable or not. You don't just do it one time. if you really want to be confident, you need to repeat your experiment quite a few times. Finally, the results, whether you did a good job or whether you just totally messed up. It's called peer review. Once the results have been through peer review, you become the authority, and other people will then look to your work. So it's tough to make it through peer review. And there are an awful lot of magazines out there, popular magazines, that are not peer reviewed, like National Geographic. They print all these beautiful articles, but I don't think I ever pushed this, did I? They print all these beautiful articles, but they're not peer reviewed. Those that are watching the tape, you say, what is the matter with this guy? Well, okay. I sure hope it's working. Make sure that I've got sound. Okay, so I've emphasized this so many times. One of the most important characteristics a scientist can have is skepticism. You don't believe anything without testing it out yourself, or at least without finding a lot of evidence in support of that. There are certain things that I can't test myself, but if I read that 10 people have done the same experiment and got the same result, I'm going to be a lot more confident. Where if I just see there's one report from somebody that said, I achieved nuclear fusion at room temperature, oh, come on, I want a little more than that. There was a guy a few years ago that said, oh yeah, I achieved cold fusion at room temperature. If we could do that, our energy problems would be solved, but nobody else was able to repeat his results. And it did make it through peer review anyway. So when somebody says, follow the science, there's nothing in science that's above questioning. A few years ago, I got into a discussion with somebody through the newspaper, letters to the editor, and he said, evolution is as firmly established as gravity and should not be questioned. And so I said, in my physics class, you know what we do? We question gravity. It exists, yeah, but why does it exist? What's going on? You're supposed to question everything. So if you're an honest scientist, you never say you proved your hypothesis. Every time my students would say, I proved this and that and the other, I said, no, you didn't. You supported it. You confirmed it. But you didn't prove anything. The only thing that's absolutely proven in science is that nothing is absolutely proven in science. Because there could always be something you're overlooking. There are all sorts of invisible things going on around us. And I'm not talking only spiritual. I don't have a way to do this, but here's something you would never know just based on your senses. Suppose that you take a bright light like a projector and you shine it against a wall and it's white. Okay, light a candle and hold it in front. All you see is a little yellow glow, but you look on the wall and you see there's all sorts of stuff going on that you can't perceive with your senses. So that's why you go through peer review. Other people may have some ideas about maybe something you might have overlooked. So if you're a chemist, you send your work to a chemical journal. If you're a physicist, you send it to a physics journal. Astronomy, you send it to an astronomy journal, and so forth. So if your work passes peer review, then it's finally published and you become the authority, and other scientists will then refer to your work. So the purpose of setting up an experiment is to try to determine cause and effect. So what you have to do is figure out a way that you're going to pretty clearly show that one thing causes something, not that 10 things cause something. So you use your hypothesis to try to decide which factor is it that you want to test. So for instance, if you want to determine whether fertilizers are going to help plant growth, you don't also change the amount of water that you give your plants. You try to make sure everything else is the same, with the exception of you can either choose how much fertilizer or what brand of fertilizer. Don't do two different things. Don't do this much of this brand and that much of that brand. You've just brought two variables in. Science is a really grinding out, boring type process, really, when you do it right. So you deliberately change only that one factor, which is called the independent variable. You know why it's called the independent variable? Because it doesn't depend on anything. The only thing it depends upon is you. You are so powerful. You choose to change it. So it's independent of everything else except for you. Then you're looking to see if something else changes in response to that. Now, I think we might have to go back into the other room next time.
Thank you, sir. Sorry for being late.
A lot of times you'll use time as the independent variable. It's not that you can control time, it's you can control when you start and stop measuring it. So it's frequently used as an independent variable. The dependent variable,
I have a question for you.
okay, can you write it down and ask at the end because I'm recording this for the
Okay.
Bible, Legacy Ministry College. Also, anybody online that's watching this, if you have questions, please write them down. And on Thursdays from 9 to 10 p.m., I'll be available to answer questions. Thank you for bringing that up. Okay, so you've decided this is what my independent variable is, the kind of fertilizer. Now my dependent variable is going to be the growth. So I monitor the plants. I don't just take one plant, I take a whole bunch of different plants and observe all of them. You also have to try to keep every other factor the same except the one that you're looking for. And then you see if the dependent variable changes. So the one you're looking for, if it's the amount of fertilizer, don't change the amount of water. Try to keep all the plants at the same temperature, same light conditions and so forth, because there could be something else that you haven't thought of that messes up your whole process. And you should also use as many experimental subjects as possible, whether it's people or plants or hamsters or whatever, because there could be individual differences that you're overlooking. So I had students that they'll take one plant and do an experiment on it. That's a terrible experiment. You need to have either a bunch of plants or else do it over and over and over. Because you can't really be sure that something was causing something else. And then to make sure that you're not overlooking something, you need to have a control group. Suppose that I'm doing an experiment to see whether plants will do better with this brand of fertilizer. Okay, so I take some of the plants and I keep them with the original brand of fertilizer they've been used to all along, and then I change to this other brand for the experimental group. Suppose they all die. That would indicate, oh, I overlooked something. You know, there could have been some kind of spores flying through the air or whatever. We can't see everything. So we just have to try to eliminate unforeseen circumstances by a control group. So the difference between a constant and a control group is the constant is a factor in your experiment. A control group is a group of individual subjects that you don't experiment on. This has been done a lot when you are testing out a new drug. Supposedly what they'll do is they'll give some of the people the drug and they'll give some of the people a sugar pill, a placebo. That's the control group. Because you want to find out if people got better and they were in the control group, maybe the drug wasn't really what was responsible. And actually there's something called a placebo effect. A lot of times if you give people a placebo, they'll feel better because they think they got the treatment,
Right.
even if they didn't. Okay, so the experiment should be repeated as many times as possible so you can be confident of your results, especially if you only had a small number of experimental subjects. You draw conclusions about whether your hypothesis was confirmed or falsified. You don't say you proved it, but you say it was confirmed, it was supported, something like that. And then you publish your results for peer review. So has anybody ever heard somebody say evolution is only a theory? Oh, that is a horrible statement. Evolution is not a theory. Once you've done your experiments and you added them to the body of scientific knowledge out there, they're part of the literature now. Other people may try to repeat your work, and if the thrust of what people are doing in that area is to find out what happens, you may work toward discovering a scientific law. Suppose that I notice that every time I throw something up, it comes down. I say, oh, what goes up must come down. Somebody else tries it. What goes up must come down. Everybody tries it. What goes up must come down. We're working on a law of science. Now, it's better if you can put numbers to it. How fast is it going to come down? So you come up with a hypothesis. I think if I throw something up, it's going to come down. And then I test it by experimentation. Well, if it goes on and on and on, it never fails a test. After a while, I might recognize, oh, okay, this seems to be a law of science. Of course, has that ever failed a test? Sure. First time we sent a rocket up that didn't come down. So if it's really, really, really bad, you might say, well, throw it out. But if it just needs a little tweaking, you might say, okay, let's modify it. What goes up must come down unless it's traveling with sufficient velocity to overcome the Earth's gravity. Okay, so that's the updated version of the, I don't know what you call that law, the what goes up must come down law. So if it's never failed a test, depending on what it's trying to do, if it's saying what happens, we say that's a law. If it's saying why it happens, we say that's a theory. In ordinary conversation, when you say theory, what you mean is a guess, right? Oh, I have a theory that if I give this girl these flowers, she's going to fall in love with me. Well, no, that's not a scientific theory. In science, a theory is a proposed explanation for something that's been tested many, many, many times and never failed a test. It may not have ever actually passed a test, but at least you're trying to test it. So you can consider it a scientific theory. But if you can't test it, it's not a theory. Doesn't automatically mean it's wrong. It just means you can't call it a theory. So the purpose of a scientific law is to describe what happens. Purpose of a theory is to try to explain why it happens. The two are very closely related, but generally you're going to have more theories than you do laws. There's one law of gravity. There's an equation for it. The force of gravity is equal to gravitational constant times the mass of the first object times the mass of the second object divided by the distance between the center squared. Okay, ready for a quiz on that? That's the law of gravity. Okay, but why does gravity exist? For that you need a theory. There are several ideas. One says that there's gravitational waves. One says there's distortions of space in the direction of a fourth dimension. I don't remember all of them, but there's multiple theories, and none of them, I shouldn't say none of them, one of them has passed the test a couple of times for a few microseconds, but we're not really confident enough that we could say, oh yeah, that's it, it's the gravity wave theory, but they've been trying to test it, so it does count as a theory. You can't test it though, it's not a theory. So there's the law of gravity. There's the equation I gave you. It tells us how strong the force of gravitational attraction is between two objects. But it doesn't say why gravity exists in the first place. For that, you need a theory. Laws can very often be expressed mathematically, and they predict the behavior of the systems they operate on, or they're describing. Theories, maybe not so much mathematical. There's only one law of gravity. How could you falsify it? Well, find out something that doesn't fit that formula. And then if it's totally wrong, you throw it out. If it's a little bit wrong, you modify it a little bit. And so Einstein, when he came up with his theory of general relativity, he said, okay, that works for classical conditions where you're not traveling near the speed of light. Near the speed of light, you need to modify it. Okay. But that was That equation is still used, the law of gravity. But there are several proposed explanations. Gravitons was the other one I was thinking of. Gravity wave, distortion of space. There has to be the potential to be falsified. Falsifiability is very important when you're doing a scientific theory. If you can't envision a test that if failed, you'd admit, okay, I'm wrong, then it's not a theory. So eventually this class is going to get around to evolution, I think. And can you propose a test to falsify the idea that some sort of an ape-like ancestor evolved into humans? No. It's something in the distant past. You can't test it. It doesn't automatically mean it's wrong, but it's not testable, and therefore it couldn't possibly be falsified no matter what you do. But suppose that there's something that you can't directly observe. There was a wonderful poem by John Sachs one time, The Seven Blind Men of Hindustan. The blind men in his poem were traveling through the jungle and they encountered an elephant. And so one of them bumped into the side and said, oh, an elephant is like a wall. Another one bumped into a leg and said, an elephant is like a tree. Another one bumped into the tail and said, an elephant is like a rope. Another one bumped into the tusk and said, an elephant is like a spear. Another one bumped into the little tip on the trunk and said, oh, an elephant is like a finger. Well, which one was right? They all were in a way. Did any of them have a complete picture? No, they were blind. But what you can do is put together what you know or what you've observed and come up with a model. Models are very useful in science. Creation is not a theory. Evolution is not a theory. There are multiple models of evolution. Just because it's not a theory doesn't automatically mean it's wrong. But when you say evolution is only a theory, no, that's incorrect. Calling something a scientific theory is a very high compliment. That means it's been tested repeatedly and never failed a test. You can't test evolution. At least not the idea that humans came from apes. There are specific aspects you can test. So there are a number of contradictory and untestable models of evolution. For instance, neo-Darwinism, the original Darwinism, said that things acquire new features as they need them. It was incorporated with a different concept called Lamarckianism. But neo-Darwinism said, well, things acquire new features because they have mutations in their DNA. Okay, can you test what happened millions of years ago? No. That's one of the models. It's called neo-Darwinism. And that says that evolution would have been a very slow, steady, gradual process going on over millions and millions and millions of years. Well, on the other hand, there are some people that look at the fossil record and say, I just don't see the transitional fossils. There are probably in excess of 1 trillion fossils. That's trillion with a T. You know, that's a lot of fossils. And out of those, we've grouped them into about 250,000 fossil species. And there's maybe 20 that anybody claims are transitions from one major type to another major type. This is out of 250,000. So you could figure, if evolution is true, we ought to have a lot of transitions. In fact, we ought to have more transitional forms than we do final forms, terminal forms. But we don't. So there have been a number of people, evolutionists, that said, okay, I believe in evolution. Fact, scientific fact. But it's not slow and gradual like Darwin said. There must have been equilibrium. Things were going along for thousands or millions of years, and then suddenly something happened, a punctuation event, like an asteroid hit, volcano erupted, a flood happened. Oh, flood, yeah, that would change everything, wouldn't it? And so this punctuation event would have disturbed the equilibrium, so it's called punctuated equilibrium. So instead of evolution requiring tens of thousands of years, it could be 1 or 2 generations. And we don't have the fossils for that because it was too fast. Then the excuse that they make on the neo-Darwinian side is we don't have the fossils because it was too slow. Well, the common thread is we don't have the fossils. Likewise, we talk about the Big Bang Theory, Oh, that's such a mistake to talk about the Big Bang Theory. It's not it's multiple Big Bang models. We can't test any of them. You can't go back and test the beginning of the universe. You know, you may come up with some conditions involving a super collider, but you can't tell that those were the conditions at the beginning of the universe. So what you can do is come up with mathematical models for how the universe might have begun. And the interesting thing is there's several dozen mathematical models and they all contradict each other. Every one shows that the other ones are wrong. They're models, they're not theories. And string theory, talking about this may be the fundamental structure of the universe, waves and so forth. Well, nobody's ever found a way to test that. Could be right, but we just can't test it. Okay, so let's talk about what some of the major divisions of science are. First, I want to talk about the things that you do experiments on. And then later, we're going to talk about the things that are so-called historical sciences, which you can't do experiments on. Physics is my favorite thing. It's a big picture of how the whole universe operates. It's all physics. The reason you're not flying away through the air is because of physics. The reason you're not sliding out of your chair is because of physics. It's all physics. It deals with forces, energy, motion, things like that. Now there's two major divisions. You have classical physics, which is the practical stuff. This was up until probably about the 20th century or so, where people would do experiments on things that observable, repeatable, testable, forces, motion, and so forth. So classical physics is what I'm going to emphasize in this class. It tends to deal with describing the causes of visible phenomena. That would include astronomy, study of motion, study of energy, heat and other forms of energy, study of sound, the study of light, the study of electric and magnetic fields, study of gravity, things like that, as far as not necessarily what causes gravity, but how it operates. Modern physics, at the very large scale, deals with relativity, things moving close to the speed of light, or at extremely high velocity, extremely high mass, time dilation. This has to do with when you have enough mass present, it affects time. I'm not going to really go into that much. Now, at the smallest scale, physics deals with the nature and behavior of subatomic objects, smaller than an atom, protons, neutrons, electrons, quarks. And why does gravity exist? Why does electricity exist? Why does magnetic fields exist? That's more the domain of modern physics than it is classical physics. Then in chemistry, I like chemistry too. I've taught chemistry for a long time. It's a study of matter. Chemistry can only operate within the laws of physics. So it's a study of matter, especially the interaction of atoms and molecules. Some of the major divisions there are going to be organic chemistry, which has to do with carbon-based compounds. So, I don't know, I'm always amused when I go to the store and they say they have organic apples. Well, all apples are organic. They're carbon-based. You're organic. You know, somebody says, I'm a Spanish American or whatever. Well, I'm a carbon American because my body's based on carbon. So organic chemistry deals with carbon-based compounds that usually come from living things. Now, carbon dioxide, that can come from a bunch of places, so that's not organic chemistry. But proteins, amino acids, things like that, yeah, that's organic chemistry. And it's really widely considered the most complicated form of chemistry, and it's also one of the most fun to me. What happened? Oh, can somebody push the keyboard on that? Just hit the shift key. Any key.
Any key.
Any key. There it is. Whoop, there it is. Oh, if it ain't one thing, it's another. Okay, so inorganic chemistry focuses on compounds that are not based on carbon. Analytical chemistry has to do with what are things made out of, the composition, the atomic structure, and some of the focus is on quantitative analysis, what's the relative ratio of carbon to hydrogen to oxygen, and others is qualitative. Is it acidic? Is it basic? And later we'll get to acids and bases, I guess. Okay, physical chemistry, it's a blur between physics and chemistry. My late friend Dr. Ed Boudreau was a physical chemist, and he knew more about physics than he knew about chemistry, I think. So you're dealing with things like energy flow. What happened? Come back here. There it is. Nuclear chemistry is also an interesting thing, especially now that we're saying, we're running out of energy, which we're not. The nucleus of the atom has unlimited supplies of energy for us. And biochemistry has to do with chemical reactions and processes that are going on within living things. So the big picture, physics. The next bigger picture, chemistry. And then moving down, okay, we get the biology. You know, it's funny, I'm certified to teach biology as well as all of the sciences, but no school has ever needed me to teach chemistry because biology teachers are a lot more common than physics and chemistry are. So biology is the study of all the aspects of life. Let me talk about practical biology. The branches that have to do with repeatable processes that are going on in the present, those are part of empirical science, experimental science, not based on speculation, but based upon actual observation and testing. So some of the major divisions, there's a lot of them. Zoology deals with animal life, botany focuses mainly on plant life, marine biology has to do with sea life. Then you also have things that overlap. You have cell biology and microbiology. Microbiology is not necessarily living things, but it overlaps with cell biology. The cells have got the most amazing things going on in them. Probably after a few weeks we'll get around to how you can recognize design in nature. And when you look at the operation of a cell, unless you're a committed atheist, you're going to go, wow! Bacteriology is very closely related to microbiology and epidemiology. A lot of different branches have to do with life at the level of the cell or life as it relates to the interaction between species and so forth. Okay, and then there are some branches that I don't even consider these science. They're storytelling. But evolutionary biology is supposedly one of the historical sciences. It tries to describe how present processes in living things developed in the prehistoric past. So biology, to me, ought to focus on what's going on right now. Now, evolutionary biology, don't really care so much about that. They just say this is how it got that way. The first living thing came into existence because of this process, and then this happened, and then this happened, none of which can be tested, and a great deal of which goes against everything we've observed. It includes topics like the origin of life, the origin of the genetic code, hypothetical ways living things could have gone from zero genetic information. You have DNA. Your DNA is incredibly complex. It contains far more information than what you realize. Suppose that I wrote a sentence, or suppose I wrote a book that had 3 billion letters in it. Human DNA has about 3 billion base pairs. A, C, G, C, G, A, C, T, T, C, C, G, and so forth. And these things can be arranged in any way to form broccoli or humans or horses or anything like that. Well, you are a human. You've got 3 billion base pairs. And they're used so efficiently, it just blows my mind. Whenever you have some kind of an invader attack your body, you have bacteria or something like that, your body makes antibodies. This is why I was really upset about all of the big push to give you a vaccination against COVID and introduce these artificially manufactured antibodies. Well, Your DNA, every vertebrate, has a capacity to manufacture about 10 billion distinct types of antibodies. 10 billion. Now you got 3 billion base pairs on your DNA. So how are you going to manufacture 10 billion? It's kind of like a Chinese restaurant. You know, you pick one from column A, one from column B, one from column C. In your cells, you have 3 segments of the DNA that are used to produce antibodies. So your cell picks one from this group over here, and one from this group over here at random, puts them together, and one from this group over here at random and puts them together. And because you have this many over here, and this many over here, and this many over here, there's actually 10 billion distinct types of antibodies that can be produced by 3 segments on your DNA. 3 gene segments. So rather than billions and billions of the base pairs, it just takes a few hundred. Well, when you're doing this, you've also got other mechanisms that have to get the antibodies to where they need to go, and the rest of the system works in conjunction with that to make them work properly. And all of this is programmed in your DNA. And then you got a brain. Your brain is the most complex arrangement of matter in the known universe. And it's with only 3 billion base pairs, but you have trillions of nerve connections up in your brain. How would this happen by accident? Anyway, there's no way to test the conclusions of evolutionary biology. And it's a good thing my head is attached to my shoulder. There it is. There's my little pointer thing. So then there's other parts of science that can either be historical or operational, empirical, experimental, whatever you want to call it. For instance, geology. I have a cousin that's a petroleum geologist. His job is to find oil in the ground. Okay, that's science. It's something that's repeatable, observable, testable. But then he also thinks I'm a fool because I don't believe in evolution, because he was trained to believe in geology. Well, there's something called historical geology, and they blend it together with the practical geology that lets you find things, mineral deposits, and so forth. Petroleum geology, mineral geology, plate tectonics, seismology, volcanology, oceanography, and meteorology, they're all closely related to geology. But then historical geology tries to piece together past processes by looking at the processes that are occurring in the present. So that would deal with topics such as the age of the earth, and I don't know, by the end of this class we may have gotten around to that. I've never taught it before. And what processes produce the present features of the earth? Historical geology is based on a statement. Has anybody ever taken a geology course? Well, they're going to tell you in any historical geology course, the present is the key to the past. That is, presently operating processes at presently observed rates are responsible for everything that's developed in the earth over the years. So if they say the present is the key to the past, how do you know that? It just is. The book says it. What if it's not the key to the past? And it's not, definitely not. The Bible says in the last days we have to watch out for that. We'll get around to that. There's no way to test that statement or the conclusions drawn from it. So that statement, the present is the key to the past. Compare that to what the Bible says. Knowing this first, that there should come in the last days scoffers walking after their own lusts and saying, where's the promise of his coming? For since the fathers fell asleep, all things continue as they were from the beginning of the creation. For this they willingly are ignorant of. This is deliberate. That by the word of God the heavens were of old, and the earth standing out of the water and in the water, whereby the world that then was, being overflowed with water, perished. Peter said, and this is a fisherman, and he knew this 2,000 years ago. He said, in the last days, look out for it. People are going to come along and they're going to say everything has always happened at the same slow, steady, gradual rate, and there's never been a flood. So look at what Peter said. The last days, scoffers are going to say, where's the promise of his coming? That is, Jesus is not literally coming back. That's just a myth. That's the first part. Second part, Since the fathers fell asleep, all things continue as they were from the beginning of the creation. Everything happens at slow, steady, gradual rates. By the way, you can download these slides if you want. I'll give you the website. So the second thing is everything happens at slow, steady, gradual rates. That's called uniformitarianism. And the third thing they're going to say is there was never a flood. They're willingly ignorant that there was a flood that overflowed the whole world. That's where you get all of the billions of years of geologic time, denying that there was ever a worldwide flood. So there are other things that are called historical sciences. Cosmology as opposed to astronomy. Astronomy deals with what's going on right now. Cosmology deals with how did it get that way. So it studies the processes that supposedly produce the universe. There are not a whole large number of cosmologists who accept the biblical account of creation. Most of them are trying to explain the universe as a result of a big bang. I'm not sure if we'll get to that in this class. Paleontology is a study of fossils. Well, if you were studying the physical structure of the fossils and things like that, that's good. That's scientific. You know, you can, to a certain extent, you could see what's the physical structure of the creature, the bone structure, the bone density, that kind of thing. But can you tell that this thing really was a mean, nasty thing that loved to go around terrorizing other animals? No, of course not. The paleontologists in general deny that there was ever a worldwide flood, the biblical account of creation and the flood. And they say, no, that could not be true. For instance, let me take a little diversion from what's in the book here, because I don't know if I'll get back to this later on. You will probably hear people say there are mountains of fossil evidence showing that humans evolved from apes, right? Well, I've done mountains of reading because I'm putting together material on paleontology, primate paleontology, apes, humans, and so forth, relating to what the fossil records say. Well, there have probably been billions of primates since the beginning of the world. You know, there's billions of humans. So primates include monkeys, apes, humans, stuff like lemurs, you know what lemurs like? They like to move it. They like to move, yeah. So there have been probably billions of primates, and you'll hear that there's mountains of fossil evidence proving evolution. Well, okay, in my reading, I've discovered how many complete primate skeletons do you think we have older than Neanderthal in the whole world? I already told you this, I think. 1. It's not even an ape. It's a lemur that was found in a gravel pit in Germany, Darwinius macellae. 1. We don't have a single complete ape fossil. I'm talking anything older than Neanderthal. Neanderthal was human. The most complete ape fossil we have is from a mine in Italy. It's called Oreopithecus. I guess they like to eat Oreos or something like that. But it's about 90% complete, but it's crushed. That's one skeleton. Other than that, we have a few that are, like 40% complete, 30% complete. There's the famous Lucy fossil that's on display all over the place. They fill in the missing parts according to the artist's imagination, but it's I think less than 30% complete. That's it. That's what we've got. The fossil record of primates consists mainly of teeth. And so somebody will find a new tooth, and they make up all of these things. If you're in academia, there's a slogan, publish or perish. You got to keep publishing new stuff to show that you're in the cutting edge of research. So there have been at least 20 articles that I've seen. I'm subscribed to a service called academia.edu. Okay, so I have access to all of these things, and there have been at least 20 articles I've seen where somebody invented a whole new species and genus of apes based on 1 or 2 teeth. Well, if you have to make a name for yourself, you have to publish. So I saw somebody criticized peer review last week, and they said, oh, this is just something the evolutionists use to reinforce each other. In paleontology, that is true. In chemistry and physics, no. So peer review is still the gold standard for testable science, experimental science. Archaeologists try to draw conclusions based upon fragments, and a lot of what archaeologists find really is garbage. You know, if you find a little fragment of pottery, it's something that somebody threw away. So they try to put together a description of what happened in the past. They might be right, but they're not nearly as adamant about it as the paleontologists are, that are saying, oh no, evolution is what happened. No, the archaeologists will say, this seems the most reasonable, most likely thing. And then forensics, even though it ends with an S, it's a singular noun. Forensics is the use of science and technology when you're trying to establish facts in historical matters, legal matters. So crime scene investigators, they try to use principles of physics or biology, determine the height of the person that killed somebody and calculate the trajectory of the bullet and find out by analyzing the mud on a person's shoes if it's reasonable that the person was really at that site. And also they might try to determine, there's actually a body farm, I think in Texas somewhere, where people who've donated their bodies to science, they'll let the bodies rot outside. And they find out how rapidly do the different kinds of insects come along and eat the bodies. It's very useful information. It still doesn't tell you who done it. On the crime scene shows, they're always trying to get a confession because all the circumstantial evidence in the world doesn't always prove that that's really the person. Yeah, they got killed. They were killed with a .38 revolver or something like that, but that doesn't say that this is the person that did it. So forensics points you in the right direction, but it can't really bring you to absolute proof and absolute certainty. Okay, let me switch to the next PowerPoint over here, if I may. There's got to be a better way to do this. Somebody tell me what it is.
He's talking to you.
Come on, come on. So how did science start? Nobody really knows for sure, but we could speculate. People didn't have TV back in the old days. So they needed something to do at the time. They'd look up the sky and say, oh, look at that. That's kind of cool. During the creation week, God said that he put the stars up there. Let there be lights in the firmament of the heavens to divide the day from the night. Let them be for signs and for seasons and for days and years. Well, the first mention of harvests and varying temperatures is found after Noah and his family. Before the flood, it seems like there might have been a fairly uniform climate. He doesn't mention anything about cold before the flood. After the flood, okay, and then seed time and harvest. So we can use the position of the stars to try to figure out when is it time to plant. There was a song that was used on the Underground Railroad in Tennessee. There was a river called the Tombigbee River. Anybody ever heard of a song called Follow the Drinking Gourd? You have, okay. Well, the drinking gourd was a reference, yeah, you've heard it from me, was a reference to the Big Dipper in the sky, the drinking gourd. This was telling the slaves who were going to escape when was the right time of the year to make your escape, and then how to go and what to look for, and so forth. So now the guys riding around on their horses, the overseers, they didn't know what this song was about. But it says, when the sun comes back and the first quail calls, follow the drinking gourd, and the old man is a-waiting for to carry you to freedom. Follow the drinking gourd. So when the sun comes back, what does that mean? Every year, if you observe the position of the sun, you're going to find out, pick the same spot on your back porch and watch and see where the sun goes down. You're going to see that as you get toward the summer months, it sets more in the northwest, and then it starts to come back, sets all the way in the west, and then goes to the southwest, and then comes back. So when the sun comes back, when it's all the way in the southwest, that's the dead of winter. When it's starting to come back, okay, we're getting close. Then you listen for the migratory birds, the quails. When you hear the quails, now the weather's going to be such that you won't freeze to death. And then it talked about the riverbank makes a mighty good road. Dead trees show you the way. Peg foot, right foot, traveling on. There was an old man, Peg Leg Joe, who was one of the conductors on the Underground Railroad. And when you find him, he had marked off on the trees a carving of a peg foot and a right foot. So you knew, oh, I'm on the right way. Anyway, the astronomy part was the key to letting you know when it's safe to go ahead and make your escape. So if you watch the stars for several hours at night, you're going to see that almost all of the stars look like they're swirling around. There's one star that doesn't. That's called Polaris, the North Star. It's called Polaris because it lines up with the pole. Most ancient observers thought that was because the stars were moving around the Earth. Well, now we realize, no, the Earth is turning. It's not that the stars are moving around. You know, I encounter people still that believe the Earth is the center of the universe. I'll tell you where the center of the universe is. Right here, for me. For you, it's your head. But as far as physics is concerned, no, the Earth is not the center of the universe. The Earth is turning on its axis, and people say, oh no, the stars are going around us. Okay. If you do some calculations and the stars are orbiting around us every night, you get as far as the planet Neptune, which is still part of our solar system, they're going to really have to be booking to get around. They're going to have to go trillions of times faster than the speed of light to make a complete circuit every night. No, we're moving. Well, of course they're moving too, but we're the ones that are moving. So you're going to gradually see every night that the stars are changing in position. In the northern hemisphere, they seem to rotate counterclockwise in the sky. In the southern hemisphere, they seem to rotate clockwise. So the stars visible in the west gradually drop down below the horizon, and a different group of stars gradually becomes visible, but then the next year you're back to the original stars. So by observing the stars, you can tell, oh, okay, the weather's going to be okay for planting. You know, there are farmer's almanac and stuff like that. They would say, okay, don't plan until such and such a month, because the position of the stars lines up with our position around the sun, and this determines our seasons. So the apparent motion of the stars is because the Earth is turning, not because the stars are spinning around us. There were a lot of things that ancient people, turn this off for a minute, did. They would connect the stars with lines, and they would say, oh, okay, look at what shape that makes. They didn't have TV. That's what they thought they saw up in the sky. There's a wonderful program, if anybody wants to download it, it's called Stellarium. That's where those pictures came from, Stellarium. Fantastic program, it's free, and you can put it on your laptop or your desktop and analyze the stars, and you can see, okay, what was the relative position of the stars on the day you were born, and what was it like when Jesus was born, and try to get an idea of the arrangement of the stars at various times. So these guys would look up in the sky, use their imagination, and think about what's up there. Okay. So the problem was they didn't just stick to observation. They also had so much mythology built into this. At the time of the Tower of Babel. There was a famous guy, the Bible talks about, his name was Nimrod. And he was
will rebel.
What's that?
That's what that meant in Hebrew, isn't it? Nimrod?
I don't know. But Nimrod was the emperor or the king or whatever of Babylon, of Babel, and Babel is Babylon, and the Babylonian Empire is from them, and they were also known by a bunch of other different terms like Chaldeans. So later on you read in the book of Daniel how King Nebuchadnezzar said, go ask all of the Chaldeans. These are just the successors of Nimrod and all of his guys. So down through the centuries, that knowledge continued, and they were part of the Persian Empire, part of the Babylonian Empire, Medo-Persian Empire, and they were very closely acquainted with Daniel and with Queen Esther, because they were all part of the official learning system of all of those empires. And one little group we know by a different name, we call them the Magi. That's the guys that showed up to see Jesus. And the reason they knew about it is because they were familiar with the Hebrew scriptures because of Daniel.
Persian.
Yep. So astronomy studies how the heavenly bodies are moving. Astrology is the belief that the heavenly bodies influence your personality and the things that are going to happen to you. You know, you still see people looking every day in the paper for their daily horoscope. But both astronomy and astrology can be traced back to the ancient Babylonians, all the way at the Tower of Babel. They kept very detailed records of the stars and planets. And the Chaldeans were sort of like the intelligentsia. They were an elite group present all the way down. And God made Abraham leave Ur of the Chaldees. So Chaldean and Babylonian was almost synonymous, although the Chaldeans were one group within the Babylonians. Okay, so the astrology, not a science, the belief in astrology depends upon something called the zodiac. So this is not, it should be spread out more, it's all bunched up, but the Earth is going around the sun. Okay, so looking past the sun this way and this way, there's a constellation back there that you can't see this time of year because the sun is blocking it. So the sun is in whatever constellation that is. And then the Earth keeps moving, and now this one is blocked, so the sun is in that, you know, Aries and Pisces and all of this stuff. It's just what constellation is it blocking. It goes left to right and also up and down. So the ancient astrologers decided to divide the sky into 12 roughly equal parts. But it's not exact. You know, there's 365 and a fourth days in a year, so it's tough to divide that exactly into 12. So they would say, okay, this one is 30 days, this one is 31 days, and it would add up approximately. But because the Earth's axis of rotation is wobbling very slightly, it's called precession, there should be 13 signs of the zodiac. NASA published an article about this not too long ago. They said there really should be 13 signs of the zodiac, including, might be Ophiuchus. Anyway, but the Bible thoroughly condemns astrology. The stars don't have any bearing on your personality and what's going to happen to you and whether you have good luck and bad luck and all of that kind of stuff. There are some heavenly bodies that occasionally seem to move backwards. So most of the bodies, we look up at the sky and we see them going around like that. But there's a few of them that don't quite match up, and for part of the year they seem to go backwards. They were wandering. Well, the Greek word for wanderer is planet. So the planets were the wanderers in the sky. The Greeks said, okay, everything's going around us, but some of these wanderers are going the wrong way. Occasionally, they go backwards for a little while and then they go forwards again. We call that retrograde motion. And the Earth was the center of the universe. It's called geocentrism, the geocentric idea, where the Earth, the center of everything. So the Greeks believed that the planets and the stars are each attached to spheres. rigid yet invisible spheres. And so these are turning, and they occasionally rub against each other. And there was an expression called the music of the spheres. Out in space, these things are rubbing against each other. And all of the stars and planets, according to the Greeks, are in orbit around the Earth. The most famous of the Greek philosophers was Aristotle, who passed on his ideas to Alexander the Great, who then passed them on to everybody else. There was a very well-known city that was a center of learning in the ancient world called Alexandria, Egypt. Who do you think founded that? Alexander, named it after himself. It's right on the Mediterranean coast of Egypt. You know, when I think Egypt, I think hot. No, it's a Mediterranean city. So some of Aristotle's teachings were that the heavens are perfect and unchanging, and since a sphere is a perfect shape, the heavenly bodies must be spheres. Even though he wanted to explain things about natural processes, he did kind of, throw the gods a bone and said the gods would want to do things that would be nice and orderly and so forth. He also said that all of the stars must be the same distance from the Earth. And I'll explain why he believed that. I want you to see what parallax is. Okay, so focus your eyes on that speaker, the black speaker up there. And hold your thumb close and blink right eye, left eye without moving the thumb. And you see how much motion there is of the thumb?
Yeah.
Okay, now move your thumb out at arm length and blink left, right, and you see there's less apparent motion. If your arm was long enough to reach there, you'd say, oh, it's not moving at all. That's called parallax. If two objects are at different distances moving with respect to each other, you're going to see parallax. And so Aristotle believed that the stars orbit the Earth. And if there were really different distances, there should be parallax between the nearer stars and the farther stars. He definitely could see parallax between the sun and the stars, every day. But he couldn't see any parallax between any two stars. So he concluded, he kind of had an egocentric view of the universe. He said, if I can't see something, it doesn't exist. I can't see parallax. Therefore, parallax doesn't exist. Therefore, all the stars must be the same distance away. His problem was he didn't have a telescope. Those were not invented for many, many, many centuries after him. So the stars seem to orbit the Earth every 23 hours and 56 minutes. So they're not in the same position every day. They're a little bit ahead, a little bit ahead, a little bit ahead. So you're going to see different groups of stars in the wintertime than you do in the summertime. So Aristotle was using logic. He invented the logic that we use today. It's called Aristotelian logic. And there are certain structures that you do. If this, then that. Okay, so suppose I tell you all dogs bark. That is, if something is a dog, then it barks. Okay, and then I tell you Snoopy's a dog. What must you conclude? Snoopy must bark. Well, is there a problem with that? Do all dogs really bark? No. There's Snoopy could have had throat surgery, he could be bashful, he could have laryngitis, or he could be a Basenji. There's a breed of hunting dogs in Africa called the Basenji that was specifically bred not to bark so they wouldn't scare away the prey. The way you do selective breeding is you kill off the ones you don't want. So the ones that don't have the characteristic you want, you kill them. And then you take the ones that did have that characteristic, breed them together. So the ones that bark less, you breed them. Of the puppies, the ones that bark less, you breed them. And finally, you got some non-barking dogs. You didn't add anything. You eliminated the capacity to bark. So the Basenjis, from what I understand, just kind of whimper, but they don't even have the ability to bark. So I told you all dogs bark. Is that right? Nope. Therefore, was your conclusion right? Nope. No. If any one of your premises is wrong, then the conclusion is unreliable. So Aristotle's believed if he couldn't see something that is parallax, and atoms also, it didn't exist. So has anybody ever heard the idea of vestigial organs? that your body contains things that used to be used millions of years ago and they're not anymore, like the appendix and the tailbone and things like that. Well, back in the late 1800s, a German guy named Wettersheim put together a list of 180 structures, and he said these don't do anything, so they're leftovers of evolution. Well, what he was saying is, since I don't know what they do, therefore they don't do anything. That's the same idea Aristotle had. I can't see parallax, therefore it doesn't exist. And of course, with the vestigial organs, we now know the function of just about all, or maybe even all, where, for instance, the coccyx, what's called the tailbone, it's the anchoring point for your pelvic muscles. And we supposedly are closely related to apes. Do apes have tails? Nope. So why would we? People say, oh, you think we came from monkeys? No, the evolutionists don't think that. They think we came from apes. There's a distinction between apes and monkeys. Monkeys have tails, apes don't. So there were about 180 things like the tonsils and the appendix and the pineal gland and so forth. We now know the functions of just about all of those supposed vestigial organs. Okay, so moving on from Aristotle. You know what happened to Aristotle? He died. Everybody dies. So Aristarchus came along about between 310 to 230 BC, and he said it makes more sense that the Earth is orbiting the sun, but he couldn't prove it. Well, he contradicted Aristotle, so he was ignored. Ptolemy, he constructed a model that was really held on to for over 1,000 years. This was all in Alexandria, Egypt. He came up with an idea about how each heavenly body moved on its own sphere, and the spheres are interacting and rubbing against each other. Very complicated, but it worked. So then the Arabian astronomers, we don't give them much credit in the United States because we just don't know what they did, but they named and cataloged many of the stars. Regal, Spica, Betelgeuse, Antares, those are all Arabic names. And they didn't propose any new models, but boy, they were really detailed. They were meticulous about cataloging the stars. Well, when the Roman Empire faded and faded and faded, the Roman Catholic Church took over as the dominant power in Europe. And there was a guy named Thomas Aquinas, doctor of the church. He believed if Aristotle said it, we have God said it, I believe it, that settles it. He said, Aristotle said it, I believe it, that settles it. Aristotle was right about everything. And since Aquinas was very closely connected with the Pope in his day, Aristotle's ideas were adopted by the Catholic Church. The earth is the center of the universe, and you better not say otherwise, or you're going to die. We're going to burn you at the stake. So then, a few centuries later, Nicholas Copernicus was a very religious man. He was a Catholic monk. He obtained a position in astronomy in Italy at the University of Bologna. He was expected to make astrological predictions for the people of the city. I don't think he was that interested in that, but he was interested in science. He developed a model in which the sun was at the center of the universe. Well, we don't think it's at the center of the universe now, but at least the solar system. So he said the sun's at the center. The math was much simpler than geocentric model, but he couldn't back it up with experimentation. And he didn't publish this until shortly before his death. Because remember, he's living in Italy and the Catholic Church is in charge, and they said, Aristotle, don't you dare contradict Aristotle. Well, another guy living up in Denmark, Tycho Brahe, it's not Tycho, it's Tycho. He was a devout Christian, and he was one of the most meticulous observers you'd ever imagine. He believed that the outer planets orbited the sun, but the sun was orbiting the earth. It's complicated. You still couldn't do any direct observations because telescopes hadn't been invented, but he designed some equipment to record the position of the planets with a precision that took centuries to match. And Tycho he was a rich guy. His family was rich. So he spent years in his observatory observing the positions of the planets at specific times every night, with the best clock he had, and I'll show you some of the equipment he developed. He was such a great observer. It's a shame he got into an argument with a cousin one time over who was the better mathematician, and they got into a duel. And Tico got part of his nose cut off. So he had to wear a prosthetic nose for the rest of his life. He still got married and had 6 kids, but he had to have a little metal nose stuck on there. Wow. That would be very attractive, wouldn't it? So anyway, Tico, he was incredible how precise he was in his measurements. These are some of the devices he came up with. It's a brass azimuthal quadrant. Big old thing. He's a rich guy. He's got a big old building for his observatory. And so it's not just this long. I don't know, 20 feet, something like that. And he'd sit there and move it. And he could record the position of that thing left to right and up and down at a specific time. And he wrote down his numbers. So every night he's gathering these observations, gathering more and more and more observations. He was able to record the position of the heavenly bodies to within 48 arc seconds. What does that mean? How many degrees in a circle? 360. Okay, each 1 degree is divided into 60 minutes. Each minute is divided into 60 seconds. So in a whole circle, you have 360 times 3,600, however much that is. It's a huge number. He could tell within 1/75th of a degree where that thing was. Okay, 1 degree, it's that much. He could go within 1/75th of a degree. It's about 1/27,000th of a circle. This guy was a genius. So he wrote numbers, wrote numbers, wrote numbers, wrote numbers, wrote numbers, didn't know what to do with them. Near the end of his life, he took on an associate, a guy named Johannes Kepler. Brahe had recorded all of this data, didn't know what to do with it, and Kepler didn't have the advantage of computer technology. He didn't even have the advantage of graphs. They weren't even invented at the time. But Kepler said he was thinking God's thoughts after him. Most of these guys were Christians, very devout Christians. So he took these vast quantities of numbers. He had thousands and thousands and thousands of numbers, and he started out with the planet Mars, which was the most difficult one. Tycho said, start with those. Okay, so he did. And he looked at those numbers and he applied whatever statistical analysis, and he finally realized, oh, that's an ellipse. Like a stretched out circle. And so once he realized it's an ellipse, okay, now the equation of an ellipse is pretty well known. That's been known since ancient times. So he found out, this is an exaggerated view, of course, he found out that the orbits of all of the planets are elliptical. Tycho died, and so Johannes Kepler got all of his data. So he found out the orbits of all of the planets are elliptical rather than circular. An ellipse is like a stretched out circle with 2 focal points. He figured out, okay, the sun is one of the focal points. I don't know what the other one is. We now would say that's the center of gravity of all of the planets. So all of the planets are affecting each other as well as the sun affecting them. And then the second law, this doesn't come across very well. If you draw a line from the sun, here's the object going around the sun. Draw a line from the sun to the object, and then pick an interval of time, 20 days, and put it on a graph. And the area in that graph in 20 days is this much. Later on in the year, same body, 20-day interval, it's going to be wider, one is long and skinny, one is short and fat, but the area is going to be the same. That's Kepler's second law of planetary motion. People think we're so smart. I saw some idiot not too long ago on Facebook saying about the ancient people, measuring the circumference of the earth with a stick. Could you? I think I might have mentioned this last time about how Eratosthenes calculated the circumference of the earth with a stick. Were you guys here? Mm-hmm. Okay. Eratosthenes, one of the guys living in Alexandria, Egypt, he was aware that there was a city about 500 miles away where there was a well, and somebody had noted twice a year there was no shadow in the bottom of the well. Because the sun, most of the time, is a little off to the side, but there are 2 days of the year, one going toward the south, one coming back, where there was going to be no shadow in the well. And he knew it was 500 miles away. So he sent a servant there to observe the well, and then he stayed behind. And on that day when the sun was at its highest point, he stood a stick upright, hang a weight from it to make sure it's upright. And he found out that the stick cast a shadow of 7.2 degrees. And he knew that other city 500 miles away, however many stadia it was, that the sun was exactly overhead. And with him, it wasn't exactly overhead. So he said, 7.2 degrees, that's 1/50th of a circle. The guy's 500 miles away, that's 1/50th of a circle. Earth must be 25,000 miles around, which is within 50 miles of the accepted value based on a stick and a well. I would say that that's some pretty amazing use of the brains God gave you. So anyway, Kepler was like this. He was such a genius. And, you look at all these numbers. He didn't have a computer, didn't even have calculus or anything like that to analyze the motions. So he came up with 3 laws of planetary motion. Here's the third one. When you compare the equation of this first ellipse and a second ellipse and a third ellipse, he found out for any of them orbiting a central body like the sun, there's a constant which depends upon the radius to the third power over the, why do I have a D? Anyway, that should be a T instead. R cubed over T squared. So he figured this out just from looking at all of the numbers. And then he said, let's put this together with another heavenly body. And he found out, oh yeah, we could calculate the orbit of any planet, any body around a central body using his third law of motion, of planetary motion. And this was done over 400 years ago. Well, we used this about, 15, 20 years ago. We sent a space probe out there to Pluto using a 400-year-old equation developed by Johannes Kepler. And we were able to predict this is where Pluto is going to be at 7 years, 6 months, 3 days, 5 hours, 14 minutes, and 17 seconds from now. This is where it's going to be, using Kepler's third law. And so they monitored the position of the spacecraft, and after about 7 years in flight, they had to fire the engine for 7 seconds to correct. That's some pretty good math. This guy was smart. So it applies to other central bodies besides the sun. The Earth can be something that things are orbiting around. Here's the moon going around. Here's the Earth sitting still. We want to put a satellite that's going to turn exactly once in 24 hours, a geosynchronous satellite, so you can watch your satellite TV. And so we use Kepler's third law to do that. I also have had some of these geniuses that say that everything else is rotating and the Earth is flat. Somebody said that the Earth is flat. I said, okay, well, how do you explain satellite TV? You got satellites in a geosynchronous orbit. They have to be at a certain distance to go around exactly once every 24 hours, matched up with the Earth. And the person said, oh, no, there's the very tall TV towers. Tall and skinny so you can't see them. Okay. All right, but after 400 years, we still use Kepler's third law. He was also the first one to calculate the distance from the planets to the sun, or the relative distance. He said, okay, let's make the Earth be 1 astronomical unit. We can see, okay, Mars is, 0.7 times as far, Venus is 1.3 times as far, and he figured the relative distance. Didn't know what the absolute distance was, but, as long as you know the relative distance, that gives you something to work with. Now, how did we come up? I'll get to how do we know the absolute distance later on. Okay, so Kepler died, And the next guy that came along, he was really, really, really famous. His name is Galileo. Galileo Galilei. Galileo Galileo. Yeah. So Galileo, he was a brilliant scientist and a devout Christian. He was quoted as saying, exact quote in Italian, "God is known by nature in his works and by doctrine in his revealed word." I like that. So the first application for a patent on a telescope was by a guy named Hans Lippershey, a Dutch guy. And Galileo read this description. He said, "I can do one of those." So he made himself a telescope. And he pointed at the sky, and immediately he found out that Aristotle was wrong. Aristotle had said the heavens were perfect and unchanging. He said, "Oh, look." What? Oh. Aristotle had said the heavens were perfect and unchanging. And, oh, wait a minute, there's a comet out there. It's changing. He also pointed it at the moon, and he found out the moon is not perfectly smooth. It's rough and uneven. The sun is not perfectly uniform, but has sunspots. Don't look directly at the sun. Put something here to have it focus on so you can see it. Otherwise, you're going to go blind. And he also found out that there are 4 moons in orbit around Jupiter that he could see through his telescope. This is a very early primitive telescope. There are many more stars in the sky than were previously thought. The Milky Way, which looks like a cloud to us when you look through a telescope, oh wait, there's individual stars. And then Venus goes through phases. Full moon, half moon, quarter moon. Venus goes through phases just like the moon does. And Aristotle said the heavens are perfect and unchanging. No, there's comets going through the solar system. So Galileo, for the first time, was able to show by experimentation, no, these things are not going around the earth. We're all going around the sun. Of course, he contradicted Aristotle, and he was condemned. And the Catholic Church brought him in and put him on trial. And they made him recant. He said, okay, I guess I'm wrong. Okay. They kind of left him alone. They kept him under house arrest the rest of his life. But there was an old story that said that when he was moving out of the courthouse, he said, "But it does move." Well, I don't know if that's true. A lot of people have talked about it. So Galileo was a really cool guy. Besides coming up with this, he also was the one that falsified the idea about heavier objects always falling faster. But the Catholic Church forced him to renounce his ideas under threat of death. And you know when that was finally reversed? 1995. Yep, the condemnation of Galileo was in place for well over 300 years. Okay, Isaac Newton. Boy, this guy invented those fig cookies. He was amazing. He's widely considered the greatest scientist of all time. Now you say, oh, Einstein was so great. Einstein was a theoretician only. He never did any experiments. Newton, he did experiments and he was theoretical. And he also wrote more on the subject of religion than he did in science. He was studying near London at Trinity College of Cambridge University, one of the most prestigious universities in the world, in 1665. The bubonic plague began to spread. So he moved to his family's estate, which was about 60 miles away. And while he was there, he did all of his mathematical work, and he discovered the law of gravity. That is, he figured out the mathematics behind it, and an apple did not fall on his head. That's a common misconception. But he wrote that he was sitting in his garden one day, and he saw an apple fall in front of him, and he said, that apple is getting pulled toward the center of the earth. If it was on the other side of the earth, it'd get pulled toward the center. The moon is getting pulled toward the center. Why are all of these things getting pulled toward the center? And he said there must be a force. And he invented this word called gravity. Nobody ever used that word before. So he discovered the law of gravity. And then he was also trying to figure out the motion of the planets. So he said, I don't have good enough math. Let me invent calculus. He invented something called differential calculus. That's where you break down a complex shape into an infinite number of infinitely small parts. Now, there was another guy, one of his contemporaries, and he's given credit also. I think he was more toward integral calculus, where you go the opposite direction. You put together an infinite number of infinitely small parts to get a complex shape. But anyway, here's something else. People think that ancient people were so dumb. Well, it wasn't until the 1600s that Newton and Leibniz developed calculus, both versions. But somebody a few decades back was doing research in Greece, and they found an ancient scroll. There's a guy named Archimedes who lived in the city of Syracuse in Greece, and Archimedes he invented the screw, the lever, the block and tackle, all sorts of stuff we just take for granted, and somebody had invented, Archimedes did. But one of the things he also invented was calculus. Somebody was looking at an ancient scroll, and they said, wait, under the surface writing, there's other writing. And so they used infrared or something like that. And they said, this is calculus. Archimedes invented both versions, integral and differential, hundreds of years before Christ. So he's a cool guy. So other people thought that somehow the sun is pushing the planets along. And Newton realized, no, things try to keep going. That's Newton's first law. Try to keep doing what they were doing unless you force them to change. And so the Earth is, and all the heavenly bodies are trying to keep going, but there's this force that's causing them to change their path and go into an orbit. He was able to rederive Kepler's laws. Kepler never knew why things were the way they were. He said, okay, here's an equation that describes a motion. Newton said, let's plug in this force called gravity, and he re-derived Kepler's laws of planetary motion using gravity as a reason. And he also discovered the first, second, and third laws of motion. He also later on invented a telescope that's the basis of most portable modern telescopes. Instead of having a lens like Lippershey and Galileo and all the other earlier guys, it had a curved mirror at the bottom. When light goes through a lens, it's going to tend to be refracted, and you're going to get a rainbow of colors. And he said, no, I don't want that effect. So he said, what if instead I make a curved mirror to gather the light and focus it on a single point? And he was able to greatly reduce the amount of chromatic aberration.
Is that the Dobsonian?
What's that?
Is that the Dobsonian kind of telescope?
I have no idea, but I need to keep going. So Newton invented this, and it's still the basis of what we use today in a portable handheld telescope. In fact, even the large observatories do use parabolic mirrors. So how do we know how far away the planets are in miles or kilometers or whatever? Now, Kepler had figured out the relative distance. This is 1.3 times as far from the sun as that is. This is 2.8 times as far. But, okay, 1.3 times what? 2.8 times what? This is kind of amazing. It wasn't until the 1830s that somebody finally developed a telescope powerful enough to actually detect parallax in stars. So light year is how far light travels in a year, which is almost 6 trillion miles. And so that's so big that instead we just use an easy number, a parsec, a parallax second. So we look at the star, and then how much distance would it have to be in order to get 1 second of parallax? It's about 3.26 light years, which is, somewhere in the neighborhood of 20 trillion miles, something like that. So the closest star, which is called Proxima Centauri, it has a parallax of about 0.77 arc seconds. That's the closest star. You need an incredibly precise telescope to be able to see even that, and that's the closest star. So that's about 4.25 light years, which is about 25 trillion miles. Only the most powerful telescopes can detect a parallax that small. If you go past about 50 light years, you're going to get 6/100ths of an arc second, which is about 1/10 millionth of a circle. You just can't trust the measurements. So 50 to 100 light years is all we can detect by parallax. Other than that, it's a whole bunch of calculations. So the stars are so far away that in order for them to be orbiting the Earth every day, they'd have to be going trillions of times faster than the speed of light. Even something as close as the planet Neptune, if it was going around every day, it'd have to be going pretty close to the speed of light. Pluto, faster than light. So, no, we're turning, they're not. Okay, now back to the absolute distance to the planets. The relative distance that have been calculated, of course, the sun, the closest one is Mercury, and then you got Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. I'm not even showing Pluto on there. So we could say, based on Kepler's laws, it's 1.3. What, you think I'm prejudiced against Pluto? Pluto is now considered a dwarf planet, and it wouldn't fit on there anyway. So we knew this is 1.3 times as far, this 2.7 times as far, but as far as what? Radar was invented in the 1930s as Hitler was moving along. The British, the ones that developed radar were actually a bunch of British weathermen, meteorologists, and they invented it, and this was used to detect when the Nazis were sending their planes in, and it really helped to give an edge to the Royal Air Force. Well, radar got more powerful, more powerful, more powerful, more powerful. Up until 1963, we didn't know the absolute distance to any of the other planets. But in the 1960s, we finally got radar powerful enough to bounce off Mars. And at the known speed of light, okay, how long did it take for the signal to go and come back? That's how far Mars is. Let's do Venus. Okay, and we got the absolute distance between us and Venus. Then plug in those numbers to Kepler's equations, and now we know the absolute distance from the sun to all of the planets. But it wasn't until the 1960s. So you notice it wasn't until after then that we started trying to send probes. The moon we could figure out pretty easily. But trying to send out probes anywhere beyond that, yeah, you need to know how far the thing is. And that's when we finally knew, this is 1960s. Ah. I was born in 52. So. Okay, and then this is one of the things that people will point out as being an error in the Bible. Psalm 19, verse 6 describes the motion of the sun. It says, his going forth is from the end of the heaven, and his circuit unto the ends of it. And there is nothing hid from the heat thereof. Talking about the sun. Well, the sun does not orbit the earth. So skeptics point this out as being an error in the Bible. Does it say the sun orbits the earth? No, it says the sun moves through the heavens. Nope. In 1965, there were some scientists at Bell Labs, guys named Penzias and Wilson, that were trying to calibrate a radio telescope. They pointed it out into space at what they thought was an empty area, and radio telescopes are going to receive radio signals rather than light. And it was giving them a little hiss. They said, well, point it somewhere else. Shh, shh, shh. Everywhere they pointed it, they got this little hiss. And they finally realized there's a microwave background radiation field out in space. It's called the CMB, Cosmic Microwave Background. And it's every single direction. So later on, somebody realized, okay, if you're moving with respect to the source of a wave, or it's moving with respect to you, there's going to be a very slight shift in the characteristics of the wave. It's called the Doppler effect. And so they realized, oh, we're moving through that microwave background field at about 1,000,000 miles an hour, based on the Doppler shift of the waves that we see. So by examining its apparent wavelength, we found out, oh yeah, look at that. We're moving through the heavens. What are we going around as we move through the heavens? The sun. So first, if you're sitting in your beach chair on the equator, I'm going to get back to this when we get to the physicsy stuff next time. Sitting in your beach chair, are you moving? Right now, are you moving? Don't look to me like you're moving. You have to have a frame of reference. Are you moving compared to what? Compared to your chair? No. Compared to the moon? Yeah. If you're sitting in a beach chair on the equator, you make one revolution of 25,000 miles every 24 hours, so you're going over 1,000 miles an hour, but you don't feel it. And then meanwhile, the Earth is moving around the sun at about 67,000 miles an hour. We take a year to go this whole distance. And then meanwhile, the sun is dragging the whole solar system at about 1,000,000 miles an hour. And what path is the sun following? A lengthy curved orbit through the Milky Way galaxy. His going forth is from the end of the heaven, and his circuit unto the ends of it, and there is nothing hid from the heat thereof. The Bible doesn't say the sun orbits the earth, it says the sun is going in a circuit through the heavens. Here's a little practical astronomy stuff for you to do. Fun thing. I did it as part of an astronomy class one time. How do we know that the Earth's axis is really tilted? If you're willing to take a year and make some observations, you can find out for yourself. Pick a spot on your back porch or somewhere where you can look the same direction every day and get a compass. Okay, so there's due west. So I watch, where does the sun go down? It's over there. It's 23 degrees north or west. And then later on, oh, it's coming back closer and closer and closer and closer. And oh, it's due west, and then it keeps going a little bit past. And it goes a certain amount past, and then it comes back. And so when you get the distance, the maximum angle from the north toward the south, cut it in half, and that's the tilt of the Earth's axis. It's a fun, easy thing to do. So at the end of June, for instance, you check, June is when the longest day is. The sun is at its northernmost position. So at the end of June, you check and see how many degrees. And then 6 months later, end of December, you check and see how many degrees. It's going to be around a 46-degree difference because the Earth's axis is tilted at about 23 degrees. I say about, approximately. And then why do we have seasons? Well, when you're in June, we're actually a little farther from the sun. But why is it hotter in the summer than in the winter? We're farther in the summer, but it's hotter. We're closer in the winter, but it's cooler. Is it that way in the southern hemisphere? When is their summer? It's when our winter is. So for us in the northern hemisphere, the sun's rays are most directly shining on us in the summertime. So we're further, but the rays are more direct. And the ocean keeps heating up, and eventually we have hurricanes because that heat's got to go somewhere. I'm so thankful we had all the rain lately. A hurricane is a heat release mechanism, and rain is a heat release mechanism. So the more rain we have, the less likely we are to have a major hurricane. Okay, so here it is June, and the Earth's axis is tilted toward the sun. We're getting most direct sunlight here. But then the end of September, 3 months later, the days and nights are equal in length, and we're going to get to the fall equinox. Equinox means equal night. And then we keep going to the end of December. We're tilted furthest away from the sun. We have the shortest daylight portion of a day. This is winter solstice. Solstice is the shortest and longest days. And then we come around into March. The sun's rays are, again, even in both hemispheres, and the days and nights are of equal length. This is the spring equinox. There's all sorts of fun stuff you could do too. If you're ever interested, you could look up online recording the position and phases of the moon. And the moon seems to form a really cool shape going through the sky. If you observe it at the same time every night, it's going to dip below the horizon for a while, but then when it comes back, it always follows the same pattern. It's a really neat thing. Okay, that would probably be a pretty good place to stop. I know it's been slightly less than 2 hours for those that are watching on video, but I don't want to get started in the next topic, and I also want to make sure that this worked out okay. So I think we'll wrap up for the night. And you guys that are watching online, I'll be available on Thursday evening. Okay, Derek, you had a question.
As far as the hypothesis, is it more common for one individual to try to follow through on his hypothesis or a group of people? You understand what I'm saying?
Is it more common for what? One
For one
individual?
individual to say they want to prove a hypothesis, is it more common for one person to try to prove it or a group of individuals?
No, I couldn't say. If you're like working at a university and you're trying to get a degree versus if you're working in a laboratory where you're given an assignment, I guess it's going to vary. Okay, did you have a question before? You were talking about the telescope?
Oh, no, I was just curious if you were talking about that, the certain kind of telescope.
Yeah.
The Dobsonian type, I think, if I'm not mistaken, is what you were referring to. I was just curious.
Well, I was just talking about a Newtonian type. You sound like you're probably more knowledgeable about telescopes than I am.
I wish I was.
Okay, well, we will stop the recording there, and I sure hope that it worked out okay.
Remember.
About to find out. Disconnect all this stuff and let's see. Stop this.